Today I'm going to talk about revealed preference methods for estimating the price of stuff that is not traded on markets. I'm going to start with some principles, defensive expenditure, travel cost. I'm going to get into that, and then we're going to have a break, and I'm going to talk about more complicated travel cost methods and about hedonic pricing. We're in week 5. Sort of almost halfway through the block on monetary valuation. First, talk about some principles for revealed preference methods. Essentially, the idea here is that we are trying to estimate the price or people's preferences, perhaps better for environmental goods and services, by looking at their behavior in so-called surrogate markets. Where the word surrogate is here, it's a surrogate for the missing market in environmental goods and services. We are looking at real markets. But that can be interpreted as related to the environment. There's 3 kinds of these surrogate markets, leading to the 3 groups of methods that I started off with. First, there can be a substitute for the environment. The market good is a substitute for something that is provided for free in the market. You can drink water out of the stream or out of the tap. That's one option. If you don't trust the quality of that water, you think there's something fishy or something toxic in the water, then you can buy bottled water instead, assuming that the bottled water is kosher, right? So here you have clearly, it's either or, you have a substitute. Where do you get your water from? So that is one option. And the methods associated with this are known as defensive expenditure, avertive behavior, replacement options, avoided costs. Those would be the sort of things that you would be looking at. The second, I was a bit enthusiastic in pressing the down button. The second option, second group of methods, is where the market is a complement to the environment. And one example here is if you want to go visit the Downs. That's a terrible example. Then most people, but not you guys, would need to drive here. You guys can just walk into the Downs, right? It's if you live on campus, it's a 2-minute walk to get into the nature reserve. But for other people, in order to get there, in order to enjoy this landscape, you would need to drive there and pay for petrol. And in this case, the market good is a complement to the desired environmental service, right? And that is a method you could, or a thing you can exploit. The methods, set of methods known using this are known as travel cost methods or travel cost model. And the third thing you can do is look at those instances where the environmental service or the environmental good is bought together in a bundle with the market good. The canonical example here is if you buy a house, you don't just buy the house, but you also buy the environment of that house. In this case, and the visuals are still terrible, if you enjoy a landscape, and I think they're growing wheat, if you enjoy that sort of landscape, you can buy a house in the countryside. And what you would find is that, and we'll actually show an example towards the end, that the surroundings of a house determined partly its value, right? This is known as hedonic pricing. and sometimes the price is the weights, and it's then called hedonic weight regressions. The good thing about this group of methods is that we're looking at the actual behavior of real people. Next week we're going to be looking at contingent valuation and contingent a contingent choice, where we're putting people, real people, in hypothetical situations. And the problem with hypothetical situations is that people do not necessarily act realistically in a hypothetical setting. So that is one main advantage. Another main advantage of revealed preference methods is that it's actually a lot cheaper to do than the methods I'll be talking about next week, because often you don't need to collect the data because somebody is collecting the data, has collected the data for you. So going back to hedonic pricing, if you want to know whether the price of a house is influenced by its environment, then you're not going to go and collect house prices, right, by going around and asking people, well, how much did you pay for your house? No, that is stored in the UK in the registry, right? So you can just look it up. It's all online. You don't need to collect this data. It is there already. Or you can ask a real estate agent, or you can scrape one of the websites for property, right? So that data already exists. So that is simply a lot simpler and easier to collect. For the travel cost method, you often have to collect data. You have to go stand near the entrance of a park and ask people, where are you from and how much did you pay to get here? But those are relatively straightforward questions, relatively straightforward surveys, and therefore easier to implement, and because they're less noisy, you also can get away with a smaller sample. So these are the main strengths of this method. Obviously, there's also weaknesses to this method, and the most important one here is that if you're looking at people buying a house, or you're looking at people traveling to the beach, and you infer their preferences for the environment, for the beach, for whatever, you're essentially inferring their use values, and typically only their direct use values. You don't buy a house because you want to preserve the elephant, right? That is a completely ridiculous connection. And therefore there is no way of inferring from this sort of behavior. Option values are difficult. Non-use values are very, very difficult to infer using revealed preference methods. There's other drawbacks. If you're looking at markets and people behaving in existing markets and inferring their preferences from their behavior in that market, the structure of that market matters how you infer their behavior. And typically, I haven't counted, but I think more than 99% of valuation studies using revealed preferences assume that the market that they're looking at is perfect. And people are well informed and rational and so on and so forth. And that makes the mathematics easy, that makes the interpretation easy, but of course in some cases it's a pretty strong assumption, right? And in the book you can actually read about some of the assumptions that you need to make in order to make this work. A third drawback is that you're essentially, by looking at markets, by inferring behavior, by inferring preferences from people's behavior, you're very much tied to a marginal calculus, right? And that means that the values you're going to derive make sense for small changes in the environment, but not necessarily for larger changes in the environment, right? That may be beyond the study. You may be extrapolating further than perhaps is permissible, right? So, strengths of these methods, but also weaknesses of these methods. Now let's look at these three methods or these three groups of methods in turn, starting with defensive expenditure. And start straight away with an example, right? This guy on the bike has a air filter in his mouth. I've never worn one of these things, but I can assume that he's not doing this because it sort of increases the pleasure of his cycle. This is, he is giving up part of the enjoyment of cycling, and he spent money on an air filter, and the reason must be because he does not trust the air in the place where he's cycling, right? This is, he would never do this if the air were pristine. If you can't see, there's a forest in the background, but what looks like a busy road on the other side of him, and he does not like the air pollution caused by the traffic. If there were no traffic, he would not wear the air filter, he would not need it, and this is clearly a way of substituting for clean air, right? And there's a real cost here in terms of the thing that he bought, but also in his enjoyment. Here's another example. This is New Jersey, this is Long Island, this is New Jersey, and this is Long Island, sorry. And in front of the coast, as you can probably see, there are barrier islands. Barrier islands are great for all sorts of things. Great for fish, great for birds, great for enjoying a day on the beach. Barrier islands also absorb a lot of the energy of waves and wind. So if you have a big storm coming from the east, then it will not hit the coast of New Jersey and the coast of Long Island. It will actually hit the barrier islands, and then the seas behind the barrier islands are pretty calm. So you have very little storm damage here, right? Not to say Hurricane Sandy that there won't ever be any storm damage, but it is much less than it otherwise would have been. So what is the value of these barrier islands? For coastal protection it is, well, if these barrier islands would not be there, then you would need to build seawalls here, dikes here, right, to protect the coast. And you can ask an engineer how much would it cost to do so, and that is an estimate of the value of these barrier islands. You could also ask an alternative question. If these barrier islands were not here, how much more flood and storm damage would we suffer? And that is another way of valuing these barrier islands. Right? Now there's two big problems with this. First is that a dike and a barrier island are very different things, right? Dikes are sort of big and stupid to look at, and they don't do much for nature. Barrier islands are actually quite enjoyable if you like coasts, but also if you're a bird or if you're a fish, they're actually quite nice places. Dikes are not, right? So it's not just that their value is in coastal protection, it is also that their value is in nature and recreation, right? So there's co-production of these things. So that is one problem. Similarly with avoided flood damage, right? Avoided flood damage in barrier islands are very hard to compare because they're working completely different dimensions, right? So that is one problem with this method or with this approach. The second problem is that this is lumpy. You're not going to build a little bit of dike. Yeah, and a little bit of dike doesn't help anyone, right? We're going to build a dike here, but not here, right? And the water just flows around it. No, dikes are sort of like lumpy investments. If you're going to do it, you would need to build a dike all along this coast or seawalls all along this coast, right? You're not going to build a bit of seawall here and then not here because that doesn't help. So there is no marginal here, right? You replace the whole thing in one go, but not a little bit at a time. And that makes the whole idea of having a demand curve and integrating under a demand curve slightly ridiculous, right? So yeah, you can do this, but it does not really work. You're looking at defensive expenditure. You can sort of like work more at the margin. If drinking water, if tap water becomes a little bit more risky, you will see, because there is many different people making sort of these lumpy decisions, you can see more and more people switching to bottled water. So there you can sort of work at the margin. Another form of defensive expenditure, if you don't like noise, is to put in double glazing in your house, if you're allowed to do so. That is, you own your place rather than rent your place. Or, and we talked about this last week, if you think that roads are not safe for cycling, you can invest in protective equipment such as helmets, right? So all these things are doable, possible. They all come with their own problems. Let's look at a particular case study, and I'm going to take you way back when, to long before you were born. We're in Milesburg in Pennsylvania in 1989. This was documented by Laughlin in 1993. And the problem in Milesburg at this time was that the drinking water was contaminated by giardia. And I mentioned giardia last week. This is, for those people who grew up on clean water, this is horrendous, right? Diarrhea, fever, cramps, nausea, and maybe worse, right? There's also cases of people dying of giardia infection. So unless you've done this from age 1, don't drink raw water, right? But the water treatment plant in Milesburg was not up to the task, and they had giardia in their drinking water. So what did people do? Oh, well, what was the welfare loss of this? Or phrased differently, what's the value of clean, drinkable water supply? So the people in Milesburg were aware of this, and the question is, how did they respond? And what Laughlin and colleagues did was they surveyed residents. What did you do when you read the news that the drinking water wasn't safe? Some people did nothing. Some people boiled their water. It was a biological contamination, so that helps. Chemical contamination, boiling doesn't help. Some people filtered their water. Some people bought bottled water, right? Here you see an example of people boiling water. Some people went to the town next door and got water from the tap there, right? Lots of options of what you can do. The next question then is, what did this cost? Some of that is easy, right? If people switch to bottled water, more expensive, often 20, 30, 40 times as expensive than tap water. If you're boiling water, how much gas or electricity? It was in 1989, so it was probably gas. How much did you spend on energy? And if you drove to one town over and got your water there, how much time did you invest in this? Right? Because taking water from the tap is actually very convenient. You just walk to the kitchen and open the tap and you have water. If you need to go to the shop to get water, or if you need to boil your water, then you invest time. And that is actually crucially important here. And here we're looking at some of the results. If we just focus on the outlay for bottled water and for energy, then the cost for some 5,500 households, don't overdo it, in a 4-month period was around $8,000. If we add in the cost of time, the cost goes up quite considerably. But then the question, of course, is how much is your time worth? If they counted up the hours, they first valued it at the minimum wage at that time in Pennsylvania, and then the 8,000 became 18,000. And then they looked at the median wage, and then it became 45,000. Right? So the main outlay here was not so much the money, but it was the time. And then the question is, of course, how much is your time worth? Right? This is a very hard question to answer. If you have a well-functioning, undistorted labor market, then the value of 1 additional minute of leisure is the same as the value of 1 additional minute of work, right? So it's your marginal wage. But of course we're not paid at the margin, right? We sort of have lumpy contracts. You work for 40 hours or for 42 hours or for 35 hours. You have a lumpy contract, right? And an average wage over that lumpy contract. And then the question here is, you get up in the morning, it used to be that you just got water out of the tap and drank it. Now you have to boil it first, so that is 5 minutes additional time that comes out of your time sleeping, right? You essentially have to get up earlier to do this. And how do you trade off between having 5 minutes more in bed in the morning or having to get up earlier? That is the trade-off that we are talking about here, right? So valuing that is actually quite difficult, but it's also, as you can see, very, very important, right? There's other problems with this set of methods. If we're talking about buying double glazing to keep out the noise, then we're not keeping out all of the noise, we're keeping out some of the noise, because double glazing isn't perfect. You can of course go for triple glazing, but then still there's some noise going on. Of course, having double glazing in your house doesn't help when you're in the garden or when it's summer and you open the windows. It is necessarily a minimum willingness to pay. Right? What you measure, it's a lower bound. If you observe that somebody has paid something, then that implies that they were willing to pay this, but perhaps they would have been willing to pay more, right? So you will always observe something below the true cost, and only between the true willingness to pay, and only if you have a lot of respondents over a large range of options, then you can truly estimate the demand curve, right? But you don't. You see my slide. I see also the next slide. But the way this thing is set up, I see the previous slide rather than the next slide. So wondering where the story is going all the time. It's sometimes very hard to to identify all defensive behaviors. So if you have a problem with your water supply, you can boil the water, you can buy filters, you can buy bottled water, you can switch to something else entirely. All these things happen at the same time. Different people will choose different mixes, different households will choose different mixes. And it's actually very hard to pin down all the possible things that people might do, because one thing that we have learned over time is that people are a lot more creative and a lot smarter than us academics seem to think. And even if you sort of like go in with your survey and you sort of say, well, these are all the things that you could have done, when you then run it in a pretest and you give the option other, then people come up with a long list of things that you hadn't possibly considered they could do in response, right? And that makes it just difficult to come up with an exhaustive list of all the things that people might do. There's all sorts of things that people might do that are hard to quantify, right? If you have a water problem, then of course you can substitute for other sources of water or hydration. But you can also say, well, I'm going to exercise less. That means I'm less thirsty and therefore I need to drink less, right? Or I'm going to eat less crisps, therefore less salt, and therefore I need less water, right? There's all sorts of things that are going on in people's behavior that may constitute a real welfare loss, but you haven't considered, or may be very, very difficult to measure, right? I showed you the example of the guy with the air filter. Another option is, of course, that you go cycling at different times. Then again, the real trade-off here is between how do you measure the relative value of doing leisure at different times of the day. Or you may decide not to go exercise at all, right? And that of course comes with other costs. Or you may say, instead of going cycling outdoors, I have one of those cycling machines indoors, right? Which give you the same sort of exercise, but of course a completely different experience. And then there's always the issue with joint products, right? Talked about double glazing to keep the noise out. Double glazing also helps to save energy, which you may do to lower your bills, but it may also, you may want to do this to help clean up the environment, right? So this needs to be taken into account. And then there's people who switch to bottled water and then discover that they actually like the taste better. And that then of course will need to be subtracted from the cost of switching, right? So you can sort of like see the principle here, but when you start thinking about it, it actually becomes very, very hairy to derive some sort of estimate of this is the value of clean air, or this is the value of clean water, right? Makes it just hard. So defensive expenditure, we look at the market as a substitute for environmental services. The travel cost that I'm going to talk about for the next, I think 40 minutes or so, with a break in between, looks at the market as a complement to the environment. And this is mostly applied to tourism and recreation, right? People enjoying these landscapes that you may not be able to see because of the projector. The travel cost method was proposed by this guy here, Harold Hotelling, in a letter he wrote in 1947. And really this is the proposal. It wasn't published in a journal, it was in a letter to the director of the park services. For those of you who do not know, Hotelling is one of the foremost economists in the first half of the 20th century. A true giant in the field. mostly doing stuff that you don't get during your undergraduate things, except for the first welfare theorem. He was the first to prove this algebraically. But he also introduced the the travel cost method. The question he was asked by the director of the national parks in the United States is, how do I prove my worth to Congress? Because at that time Congress was trying to cut the services, trying to cut the payments to the national parks, much as the current government is doing in the United States. And Hotelling answered as follows: let concentric zones be defined around each park so that the cost of travel to the park from all points in one of these zones is approximately constant. The persons entering the park in a year, or a suitably chosen sample of them, are to be listed according to the zone from which they came. The fact that they come means that the service of the park is at least worth the cost, and this cost can probably be estimated with fair accuracy. If we assume that the benefits are the same no matter what the distance we have for those living near the park, a consumer surplus consisting of the difference in transportation costs, or nowadays you need to call the cisportation cost, right? The comparison of the cost of coming from a zone with the number of people who do come from it together with a count of the population of the zone enables us to plot 1 point for each zone on the demand curve for the services of the park. By a judicious process of fitting it, it should be possible to get a good enough approximation to this demand curve to provide through integration a measure of the consumer surplus resulting from the availability of the park. It is this consumer surplus, calculated by the above process, which measures the benefits to the public in that particular year. This is the zonal travel cost method, right? And Hotelling spelled it all out. There's two things here. One thing I already said, right? Nowadays we're not allowed to say transportation because of the word trans. The other thing is that Hotelling writes not about the consumer surplus, but about the consumer's surplus. This was before economics had moved to a representative agent that somehow occupied a range of potential behavior of that representative agent. And then you have a demand curve for the same person at different sort of alternative universes. That is really what a consumer surplus is. Hotelling said, no. We are talking about a range of different real people, not hypothetical representative people. So that is why there is a consumer's surplus, not a consumer surplus in Hotelling's time. And this is probably more accurate than what we do now. Anyway, so that's the travel cost method. What can you use this for? You can use it for looking at sites, recreation sites. And you can look at them, opening them or closing them, or changing their quality. Or you could look at changes in access, right? If there's a car park there, we can charge more for parking or start charging for parking. Typically, and that is where Hotelling started, this is done for a single site. And then after the break I will talk about if you have multiple sites that are competing with each other, how would you deal with that? And you can do that like Hotelling proposed by zones, or you can do it individually. And essentially the question is, how many trips are made to a site at a particular cost? So first we need to establish that we can actually do this. So let's assume that we have an economic agent who wants to maximize utility, and utility depends on visits to an enjoyable site, let's call it R, and the rest of consumption, let's call it X. We're subject to a money budget, that is the amount of time that we work times the wage that we get, that is our income, We can spend it on X, and we assume that the price of X is normalized to 1. So this is overall consumption, and we can spend it on recreation. And this is the number of visits to the park, and this is how much it costs to visit the park, right? So this is the money budget. We also have a time budget. That is this 24 hours in the day. We can spend that working, or this is a pretty simple model. We can go hang around in the park, right? This is how often we do that, and this is how much time we spend there. Now, we have, I can't read, we have a money budget and we have a time budget, right? What we can do is define the true cost of visiting the park as P, right? We can just call it P, right? The true cost of visiting the park is how much it costs to get there, C, plus how much time we spend there, and then the opportunity cost of time, right? So this is the true cost of our visit. Now, we have this thing here. We can multiply that on both sides of the equation with R, right? Nothing has changed. And then bring WTRR to the other side of the equation. And now we have an expression for CR. And what we see is that in our money budget, we have CR as well. So we can substitute CR that we see at the very top with this expression here to find that this is true. Now what we also have is that TW plus RTR is equal to T. So we can bring this to the other side of the equation, substitute the second line here to have this budget constraint here, that wait time times the number of hours in the day or number of hours in the year is the true cost of visiting times the number of visits, and then our composite other consumption. And this is a money time budget. And now we're back to standard micro, right? We are maximizing utility subject to a single budget constraint, maximizing utility subject to a single budget constraint. So we form the Lagrangian, here we have it, and then we have as first order conditions, two of the three here, that the x is equal to lambda. That is the marginal value of consumption is equal to the marginal value of income, our budget constraints. This is how much we can spend. This is the standard condition that we have. And what we have for du dr, that is our choice about how often we should go visit the park, is first partial derivative of this thing is du dr, and then the first partial derivative of this thing is lambda t. Bring that to the other side of the equation to get rid of the minus sign, and what we have is that the marginal value of recreation is equal to the shadow price, our budget constraint, how much money we have, times the relative price of doing this, right? It's a relative price because the price of x is 1, right? So p over 1 is p, right? So recreation is just an ordinary good, right? There is nothing special about this. If we are prepared to make this particular substitution, right? Essentially, if you are saying time is money, then recreation becomes a standard economic good that you can just stick in your micro and derive a demand curve for. And that is the key assumption that we're making here. Time is money, right? Through this equation here and then through this That means we have a demand curve, and that means that we can integrate under the demand curve and find the consumer surplus, because it's no longer 1947. Right? So, what did Hotelling propose? We're interested in the value of site 1. There's only one. It's green. It's in the middle. And what we is draw concentric, not too fast, concentric circles around this, where the people here can get to the place, and with a 5-minute walk, the people here need 15 minutes to get here, the people here need 25 minutes to get there, and so on and so forth, right? That is the idea. And that is how the zones are defined. Then what you can do is something like this. This is a hypothetical example, absolutely. So we are interested in this park. In zone 1, 2 million people live, right? So the concentric circles were a good bit bigger than I suggested on the previous slide. And of those 2 million, 15,000 visit per, let's make it per day, no, let's make it per year, right? Because otherwise we have lots and lots of people in this place. And let's assume that in zone 1 it costs a tenner to get there, right? You need to normalize this, right? So 15,000 out of 2 million visit, so that is a rate of 7.5, right? In zone 2, a little bit further away, it costs 15 quid to get there. In zone 3, it costs 20 quid, 25, 30, right, in zone 5. And in zone 2, 48 out of 8 million visit for a rate of 6. In zone 3, 250 out of 2.5 million visit for a rate of 4.5, and so on and so forth, right? So this is the data. These are the zones where travel cost is relatively homogeneous for these 2 million people and for these 8 million people, and the costs go up as you're further and further away from the park. So this is what we observe. I define the visit rate, and you can estimate a linear model to this, right? Where essentially what you say is that the visitation rate goes down as the costs of visiting go up, right? The price is higher, demand is lower. And in this case we have this particular fit, 10.5 minus 0.3 times the price. And you can estimate this with ordinary least squares, right? Where you minimize the square distance between your observation and your prediction, right? You find those two parameters, alpha and beta, so that the difference between your predicted R and your observed R is minimal, right? That's what you do in ordinary least squares, for those of you who haven't done your econometrics. Once you have this model, we say, well, this is the relative number of visitors as a function of the cost of visiting. You can play around and say, what if we raise the entrance fee by £5, so that the costs become 15 and 20 and 25 and 30 and 35, right? That's what I think I did. Yeah, I raised the price by 5. Then obviously demand drops, right? It goes from 9 to 6, and from 6 to no, it goes from 7.5 to 6, from 6 to 4.5, and 4.5 to 3, and from 3 to 1.5, and from 1.5 to 0, right? The people in zone 5, if the cost goes up to 35, say, I can't be bothered to go there, it's not worth it, right? We have a new rate. Then you can multiply that with the population to come with predicted number of visits, and that is what we do. And then you can try this with different values of your entrance fee. So this is the original situation, 153,000 people visit. Then you raise the price by 5, the demand falls to 78, and so on, falls to 0. If you raise your entrance fee by 25, it's a bad idea if you want to keep getting people to the park, right? So we have a demand curve like this, or we have 5 points on the demand curve, and then we can draw a line through that and integrate under it to find the consumer surplus, right? So that is the zonal travel cost method. As I said, this was proposed in 1947. The book tells you when it was first implemented. It was sometime in the late 1950s that people first did this, but I forget the exact date. A consumer surplus in this case is slightly over 1 million. All sorts of things you could have done differently, right? I assumed that R is a linear function of C, but we could have taken logs on both sides of the equation or on one side of the equation, or you could have assumed a quadratic form, or and so on and so forth, right? That is an empirical matter. What is the best fit to your data? I suggested using OLS, which is convenient but wrong because you can't have fewer than 0 visitors, right? It's not that if the price goes high enough then all of a sudden the park starts producing people that leave the park, right? That doesn't work that way. So if you want to have to model that doesn't predict fewer than 0 visitors, then you should switch from OLS to Tobit, right? That's typically something you get in the masters only. Okay. There's other things wrong, right? What Hotelling proposed and what people initially did, and that is a matter of data availability really, is that there are these homogeneous concentric circles around the site, and everybody in that concentric circle is assumed to be the same. That is a very convenient assumption to make, but obviously it's not true, right? So people have switched to individual level data, where instead of putting people in a circle and sort of say everybody who lives in Brighton is the same, and the travel cost from Brighton is the same to say the Seven Sisters, regardless of where you are in Brighton, which is a ridiculous assumption to make, right? What you can do nowadays is that you can do this with individual level data. If you know where somebody lives, you can work out the actual travel distance between the site where they're going and the site where they started. It used to be that you would take the Great Circles distance, that is as the crow flies, but of course people can't fly. But nowadays with Google Maps and those sort of tools, you can actually calculate the shortest distance over the road to get there. And Google will also tell you, if you take public transport, how much you're paying for this, right? So basically what you now have, if you know where somebody is and you know where they came from, you can work out how long it took them, and you can work out how much they paid, right? So, but this is not that Hotelling did not want to do this, but he could just not imagine the technology that we have in 2025, right? So this is just technological progress, right? Of course, what you also want to include in your model are such things as, do older people behave differently than younger people? They typically do. Do men behave differently than women? Do rich people behave differently than poor people, right? And the answer to all of these questions is typically they do. The big problem with the standard travel cost method, as I just sketched, is that it does not take into account competition. I assume that there is a park, and the question is, what is the value of this park? And I'm going to derive that value from visits to that park. But most cities have multiple parks. Most people have multiple places where they can go enjoy themselves, and the substitution, the competition between these things is simply not there in this model, right? So that's what we're going to do after the break. We're going to look at multiple sites at once. And that then also immediately allows for looking at such things as site quality, right? Because if you look at a single thing, then you're not quite sure what determines the value of this thing. If you only have Brighton Beach, do people go for the sea? Do they go for the gravel that is there? Probably not, because nobody likes gravelly beaches. Do they go for the amenities that are around there, the bars and the restaurants and the pier and those sort of things? All those things are bundled together, and you don't know what drives the value of Brighton Beach. But if you then have Brighton Beach and New Haven Beach, right, which look very similar, but New Haven doesn't have the pier, then you can sort of say, well, the additional value, the reason that Brighton Beach is valued higher by presumably younger people or people with sort of teenage kids is because the pier is there, whereas New Haven Beach may be more attractive to people with young children or people who just want to enjoy the quiet of the beach, right? Brighton Beach is of course also much more crowded than New Haven Beach. So if you have multiple sites, you can actually break out what drives the value of this particular environmental amenity. Travel cost method cannot account for non-use values, right? People go to the beach because they want to be on the beach, right? Not because they want to preserve the beach for their children, right? That's just nonsense. Opportunity cost of time is very difficult in all these things. I did it at Giardia. We assume that the trip is a cost, which is true in many cases. You go someplace and you're putting up with the travel time to get there. But if you're traveling with friends and you're having lots of fun on the way, then the trip itself is part of the experience, right? It's not a cost, it's actually part of the amenity. And if you go to further away, right, I've been talking about Brighton Beach, and if you sort of like would interview people on Brighton Beach, where are you from? Then you would find that there's a lot of locals and there's fewer people who are further away, and very few people who came all the way from Australia to go to Brighton Beach, right? That is your demand curve, right? The cost is low of getting there. If it's very nearby, then you go. If it's very far away, you don't go, right? That is a demand curve. But if you're talking about Bondi Beach, right, in Sydney, you would find few Australians on Brighton Beach, but you would find more English people on Bondi Beach because it's such an attraction, right? But if you ask these people, why are you here? Some of them will say, well, Sydney nightlife, which includes the beach, is one of the reasons that I went all the way to Australia, but I also wanted to see the Opera House, right? And I'm also going to drop by the Great Barrier Reef, and I may have a side trip to Adelaide or Melbourne, right? And you cannot say that the 24 hours you spent in the plane getting there and the £2,000 that you paid for that trip is all because you wanted to go to Bondi Beach, right? It's one of the reasons that you may want to go there, but it's not the entire reason. And then you need sort of to attribute the cost of traveling there to its multiple purposes, right? And that makes it all very, 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 very complicated. But in principle, you can see this work. We're going to pause for 10 minutes, and then I'm going to talk about random utility models, which doesn't sound quite as daunting, isn't quite as daunting as it sounds. I'm going to continue a little bit with the travel cost method, talking about random utility models. Random utility models essentially take away the first concerns we have, that is competition and site quality. It doesn't take away the rest of the concerns that I listed before. So what do we observe? We observe an individual going to one park but not to the other, and we can reasonably assume that those other parks are within reach of this particular individual. What we can deduce from that is that the utility that individual I derives from going to G, the park that she chooses, is greater than the utility she would have derived had she gone to another park, right? Another park J. So that is something we can infer from this choice, assuming that C is rational, right? And informed about the quality of the different parks. Now, not everybody is the same. So what we can do is decompose utility U into a deterministic part and a stochastic part epsilon. So we replace U by V. This is the deterministic part, and then we have a random component here. We do the same on the other side of the equation, and we have this particular condition. And then we can write that utility, that deterministic component, as a linear function of all sorts of everything. In this case, it's the travel cost there and the income of this particular person, but you can add whatever you want to this. Importantly, because this is what we're interested in, you also include measures of the quality of the site. If we're talking about parks, whether it's fields versus trees, whether there's a fountain there, whether there's a kiosk there where you can buy beer, and so on and so forth, right? All that would enter into Q. And you can measure these things or include these things. Breaking my mic. You can include as many things as you think are relevant and for which you have data, right? So that is an assumption you make, and then you assume that that stochastic term follows a Gumbel distribution, looks like this. The reason you want to do this, because otherwise you can't do the math, right? If you assume Gumbel, you can do the math, if your name is Dan McFadden. And then we have the complete model. If you assume Gumbel, then the probability of choosing G is this expression here. It's the exponent of your deterministic utility, and whatever you choose to include in there, income, age, whether there's a kiosk, and so on and so forth, divided by the sum of the exponents of all alternatives, right? So this necessarily lies between 0 and 1, right? You can go there, you can't go there. Typically it lies somewhere between 0 and 1. So this follows from the assumption that it's a Gumbel, right? Then what you need to do is do this for all parks that are there, and then you have the likelihood function for all your observations, and then when you want to find the maximum likelihood by varying the parameters in your deterministic part as well as the variance of your stochastic part, so that you predict where people go. Now, I am fully aware that the single honors did not do multinomial algebra last term, and I'm fully aware that the joint honors haven't done OLS even at this point in time. Essentially what you do is you try to find these parameters, beta 0 and beta 1, and if you have other indicators, beta 2 and beta 3 and beta 4 and beta 5, right? So that the predicted probability, do I go to Brighton Beach or do I go to New Haven Beach, is as close as possible to the observations, right? The observations are 0, 1. You see some people in Brighton Beach and you see some people in New Haven Beach, right? So you guys are all young, you're all on Brighton Beach, I am much older, so I am on New Haven Beach, to your delight, right? You won't see me there. Right, so you have zeros for New Haven and ones for Brighton, and for me it's the other way around. And then what you want is to build a model that gives you, that predicts you, for you, a high probability to going to Brighton Beach, and a low probability for me, right? And vice versa for New Haven. So that is the model prediction, and that depends on your parameters, and in this case it's very simple. People below 30 go to one place, people above 30 go to another place, right? Then you have a perfect prediction. Of course, there may be a few people from New Haven who go to New Haven, young people from New Haven who go to New Haven anyway, right? But you have a prediction of who will end up where, how people are sorted, and you want to choose your parameters such that that prediction comes as close to the observation as possible. The observation is you're there or you're someplace else, right? And the prediction is 75 probability you would go there, 25 probability you would go to the other place. That is a decent prediction. If you can tune your parameters such that it becomes 90% versus 10%, you have a better prediction, right? So that is essentially what you do in maximum likelihood. It's a bit more fancy than that, but basically that's what you do, right? You minimize the distance between the predicted probability, which lies somewhere between 0 and 1, and the observed realization, which is either 0 or 1, right? Clear? Now we have a model that says what is your probability of going someplace depending on the quality of that place. And then you can start playing around with those qualities and around counterfactuals, right? If we find that having a kiosk that sells beer in the park is one of the main reasons that people go there, we can sort of predict what would happen if that kiosk closes or stops selling beer, right? You could also, if you have a new site, you can say, well, these are the observable characteristics of the proposed new sites that compares it, makes it comparable to existing sites, and then you can predict the probability of its attractiveness to people, right? Importantly, the number of trips is not explained. You need a separate model for that. And we also, otherwise the model doesn't work, we assume independence of irrelevant alternatives. So going back to parks, probability of your visiting either Wakehurst or Sheffield, the relative probability of Wakehurst versus Sheffield should be independent of the question whether you've ever heard of Standen or not, right? If you like Wakehurst better than Sheffield, then you like Wakehurst better than Sheffield regardless of whether you know of the existence of Standen, right? And this is an assumption that is baked in. This is on the one hand, this seems like a very straightforward assumption and one that you must make, but not if your utility function is not to go to the place that you enjoy most and go there as often as you can, but you have a love of variety, right? If your objective function is to go to as many places, different places as possible, and sample them all because you like to experience new things, then your probabilities of going to places may actually depend on the opening of a new site or you learning about a new site, right? So this may seem, yeah, we need to assume this. We do assume this in multinomial logic, but not necessarily what you want to assume in every case, right? And you see that, for instance, in international tourism, that there are people who have got it in their minds that they need to visit as many countries as possible, regardless of whether that country is at all interesting or attractive. They just want as many stamps in their passport as could possibly fit in their passport. It's just not the sort of behavior that I share, but there's clearly people out there who are like that. So you can do this for a great many things. The example I have here is South Africa, or more specifically KwaZulu-Natal, right? Yeah. And there's 4 game parks there. The names will pop up on the next slide. And the question is, which is the most attractive? What is the total consumer surplus? There's actually a whole bunch of no. Yeah, these are all parks in KwaZulu-Natal. But the one we're going to talk about 4 of them because they are for. Don't do that. Phone is still okay. These are the wildlife parks, and if you want to see wildlife, then you need to be there either at dusk or at dawn, which means, and they're pretty far away, which means that you have to spend the night there, right? Because it's not a day trip. You can arrive around 12, around noon, but then they're all asleep, and then you have to leave at 3 again in order to go back home, and you haven't seen anything. So you need to spend the night there. And that means that there's actually proper registration of visitors, right? There is administrative data of who was there, how much they spent, where they're from, because you need to fill out the form once you're there. And there's various accommodation options. You can go in a luxury hotel, you can go in a tent, and all sorts of things in between. The question you can ask then is how much welfare is derived from access to the park, how would this change? How will revenues change if we change pricing, right? The 4 sites studied are listed here. My Zulu is absolutely hopeless. It's quality differentiation between the prices, right? Some have a luxury hotel, some just have very basic tents. Some places you can see giraffes, in other places you can't. The study focused on the locals, not the people who flew in from Europe to go there. They typically go to other parts of South Africa. And starting point was administrative data. So at the very beginning I said, well, for this sort of studies you don't have to collect your data, right? Because the hotels and the parks collect this data for you, because that is in their administrative system, right? And you just need to convince them to give you this data. But this was done a while ago, so they selected 1,000, and for those 1,000 they worked out in detail where they were from and how much they paid and how long they traveled, right? And that is because when this was done you needed to do that by hand. Now you write a script in R that does it for you, and you could have done all 26,000. So what do we know? We know the address, we know the size of the party, we know the accommodation type, we know how long they stayed, we know which park they visited, we know how much they paid to get in, we know how much they paid to spend the night. And then found home, and then also match this not to the individual income, South Africa, race, and those sort of things, but match that with the socioeconomic data, right? These are from a poor neighborhood, these are people from a black neighborhood, and so on and so forth. Travel cost, calculate door to gate distances, assumed how much fuel they would have spent, and this was all observed. The time again was assumed, well, if you're from this neighborhood is poor. From the census we know the average income, and that is what we're going to assume to be your opportunity cost of time, right? That is what they've done. And you sort of like, oh, this is pretty hairy at some places, right? You would want to do this better, but this is what they could do. And then you can estimate the relative demand, and then you can also estimate what if we would close this park, how much would welfare reduced? So if we close Itala, because that's the easiest to pronounce, the welfare loss would be $20.37 per trip, right? If we close, and this is a click sound like, Luluwe and Umfolozi, right? The welfare loss would be 106. And you can do this, and then you can also work out the total consumer surplus of these sites. And you also see that it's not additive, it's more than additive, right? If we close this one, it's 473. If we close this one, it's 300. If we close both, then actually the welfare loss is much more than the 700,000 that you see here. It actually goes up to 1 million, right? So there's superlinearity, there's more than additive. So that is what you can do with this method. Powerful in some ways. You need sometimes to pile assumption on assumption in other directions. And it can only be used for recreation, right? Because that is why people travel. It cannot be used for other values. So final method is hedonic pricing. This is Dorchester. And the question is, what is the value of this particular house? And the value of this house is determined by all sorts of things, right? How many bedrooms and bathrooms there are. Is there parking nearby? Absolutely not. This is Dorchester City Centre. Has it original features? Absolutely. This house is from the 1600s, if I'm not mistaken. So these are all things that directly related to the building, right? But then there's other things going on. It sits on a little canal, and you may enjoy living near water. Or you may say, well, water, smelly, mosquitoes, and so on and so forth. I hate living near water, right? But obviously it affects how much you would be willing to pay for this building. Parks matter. Aircraft noise matters, not in Dorchester because you're far, far away from any airport. And the quality of the schools matter, and so on and so forth. So you do not just buy, you do not just buy the house, you also buy everything around that house. Crime rates, and so on and so forth. That's what I just said. So what you want to do is estimate the price of a house as a function of all these characteristics. And There's various ways of getting that data. One of the ways is going to Rightmove, right? Where you would find every house that is currently on the market. You would find its asking price. And you would find a long list of descriptions of the house. Everything that real estate agents think are important. That includes floor area, obviously, number of bathrooms, and so on and so forth. If you go on, not you guys would not be on Rightmove, right? Because you're not on the market. You would find the nearest bus stop. You would find the nearest train station, and so on and so forth. That's all listed there. You would find a description of the neighborhood. And all sorts of other things there as well. Nowadays, they also need to disclose flood risks and air quality. I don't think they do, but you have the exact location of the house. So you can then go to the site of the Environment Agency, where you would find in great detail air quality data for every location in the United Kingdom, right? No, in England and Wales. The Environment Agency, you would need to go to the Scottish and the Northern Ireland equivalent to find the air quality there. But you can find this, right? Similarly for water quality, and you may be able to find scenic views if you go to Google Maps and then click on the little thingy that shows you pictures of around. You can sort of like work out how does it look like from this house, what can you see, what can't you see, right? So you can work out a pretty detailed picture of what you are buying, essentially, right? And a lot of that is GIS data. These are 4 maps of London. This is road noise in London. It's pretty even, right? This is airport noise. This is very uneven, as you can imagine, right? Heathrow is here, and this is landing and takeoff. This is air quality in London, and the bluer is better, and the lighter colors are worse. So you sort of like see the road network, right? This is where a lot of the air pollution is. In the city centre there's a lot of air pollution, but then if you go to the outskirts of London, this is Greater London, of course, this is the M25, you see that air quality gets a lot better, right? This terrible map is not Pollock. This is the land use map. So in black it's built up, in light green it's agriculture, darker green is forest, blue is water, red, I think, is industrial, I'm not sure. And you see, if you have good eyes, which you don't, well, you have good eyes, but the projection is bad. You see the Thames going through London, right? And you can get all this data, right? So if you know that the house sits here, you know it sits on agricultural land, right? The sort of the brown, this is pasture, this is agriculture. I'm not mistaken. So you can estimate the demand curve, right? And here we see an example of that. This is an example from the United States, but I am not sure which city we're in, but that doesn't matter, or what year we're in. So you observe house prices, you observe all these characteristics, and then you can just estimate this equation, right? Sale date, positive, the later you buy a house, the more expensive it gets, right? This is general price inflation. Older houses sell for less, makes sense. Bigger houses sell for more. Houses with more bathrooms command a higher price. Houses with a pool are more expensive. Houses with fireplaces are more expensive, right? All this makes perfect sense, right? Then, houses that sit in neighborhoods with lots of crime are cheaper, right? Houses that sit in neighborhoods with good schools are more expensive. Houses that sit, this is the US, houses that sit in white neighborhoods are more expensive, right? Houses that sit in sort of like less densely populated areas are more expensive, and so on and so forth. So these are sort of social environment, right? Then we also have the natural environment. Distance to beach, the further away you are from the beach, I think we're in California, the cheaper the house is. That doesn't make any sense. What does make sense is that the closer you are to the beach, the more expensive the house, right? That makes more sense when you say it like that. Then here we have air quality, total suspended particles. That is a general measure of air quality. The dirtier the air, the cheaper the house. And here we have not total particles, but just nitrogen dioxide particles. The more of that stuff is in the air, the cheaper the house, right? So here we have a direct measure of how much people are prepared to pay for cleaner air. And that is what we were after, right? Now, this has been done in many different places for many different environmental characteristics, and it seems pretty reliable. There are a whole range of assumptions here, right? What we assume is that people express their preferences through the market, and we assume that that market is somehow in equilibrium, because otherwise you cannot really interpret their behavior. So we assume that people are informed about these things. And there's a number of experiments or recent studies that have actually worked on this particular assumption. One of the things that happened in the United Kingdom, I think about 10 years ago, is that the seller was forced by law to disclose whether or not a house was in a flood-prone area. Before that, you needed to rely on local information, or you needed to be an engineer that you could read the landscape, or you needed to know the locals. Is this house prone to flooding? Or you needed to have an honest real estate agent. But many people did not know the flood risk of the house that they were buying. And if you ran these hedonic regressions of house prices on flood risks before this law came into effect, you would find an insignificant coefficient. That is, flood risk does not explain house prices. Then they changed the law, I think it was 10 years ago or so, and if you run your hedonic regressions after the law changed, you can actually see that flood risk suppresses house prices, right? Nobody wants to get their basement flooded. I've been there, I can tell you it's not fun. So that is important, right? Environmental characteristics that are not observable to the market cannot affect the market, right? People act on the information that they have. So that is important. Of course, people also need to know about quality of property nearby and so on and so forth. That is not such a tall assumption, because this is probably one of the biggest things you're ever going to buy in your life. So people really make informed choices, right? When they buy a house, they really study the house and how much they're paying, and the market and the environment and so on and so forth. No transaction costs as a tall assumption, immediate equilibration and so on and so forth. These are actually key assumptions. Sometimes people ask and say, well, this is the list of regressors that you have, but there's nothing about the buyer and there's nothing about the seller. Why is that not included in your regression? And the answer is because we assume that the market has cleared, right? So what you see here is that houses near good schools go for a higher price. And this is a consistent finding that you find in a great many empirical studies. And that makes perfect sense. But there's no such thing as the buyer has school-going children. Well, you may find it odd, but it's not at all, right? So in England we have this, it will soon be abolished, this system for primary schools. Some are excellent, some are good, and you have the offset ratings. I believe there's 4 or 5 of them. And in the countryside in Sussex, if you live near an excellent school, your house is 10-15% more expensive than if you live near a good school, and that is £100,000, right? Now, we live near an excellent primary school, and we did pay that additional £100,000 to get our kids through an excellent primary school. But our house price did not fall by 100,000 when the kids went to secondary school, right? And the reason for this is that we can sell the house to another couple with young children that are about to go to primary school, right? So the fact that our children no longer need the primary school does not mean that our house all of a sudden is worth 10-15% less. It's entirely irrelevant. What matters is, and what matters is not the buyer of our house, not that it's for sale, whether the buyer has children in that age group. What matters is that there are parents, potential buyers in that age group who would be willing to pay the price. So whoever is going to buy the house from us will have to pay the premium of living near an excellent primary school, right? So the characteristics of the buyer and the seller, because we assume that the market is in equilibrium, do not pop up in a hedonic regression, right? Of course, if the market is not in equilibrium, if the market is very thin, then you sell your house to whatever fool comes along, right? Rather than to an informed buyer. Good things about this method is that we have tons of data, right? Really tons of data, some extremely good quality data. And it's been applied for basically everywhere, because we have shown, or people over the years have shown, that property markets really respond to all sorts of things: noise, air quality, the view from the bedroom, whether you can see trees or not. All those things matter. There are problems, as always. You can only apply it to things that directly affect the price of the house, right? So if you're looking at the housing market in England, you're not going to discover the value of African elephants, right? Forget it, right? It's just not there. And of course, people must be aware of these environmental characteristics. There is one deeper problem, or you can call it a strength, and that the environment doesn't just affect house prices, it affects wages too. Now this may sound a bit strange to you, but it's been shown empirically over and over again. And you'll be on the job market, most of you, in 1.5 years' time, right? And just imagine, right? Somebody offers you a job in Bristol. And you think, great, Bristol is a wonderful place to live. And then somebody else offers you a job in Aberdeen, and you think, like, really? And you would really demand a higher wage to live in Aberdeen, which is dreadfully boring and incredibly far away from everything and everyone, right? And you would really demand a higher wage if somebody wants to send you to Aberdeen. or a place worse than Aberdeen, Moormansk or something, right? Somebody were to offer you a job in Paris, you would go, yippee, when can I start, right? And some people say that before they ask about, so how much does it pay? So the environment really affects wages as well. And you will say, so here we have a second market where we can apply hedonic methods too, right? And people have done that, and that is a good thing because you have more information. And the problem is that house prices are affected by wages, and wages are affected by house prices, right? In places where housing is expensive, you would demand a higher wage. And if wages are higher, then people start bidding for houses and the house price goes up, right? So those two markets are not independent of each other, and both are affected by the environment. And that creates a challenge with the econometrics that we typically only deal with at PhD level, right? But it can be solved, but it creates issues. So can this be applied? I don't have a whole lot more to say, and I don't think I can say a whole lot more. Let's look at the amenity value of English nature as application. Essentially the question is, what is the value of living in or near desirable natural areas? John Gibbons, I'm pretty sure, did this in 2011 as a contribution to something we're going to talk about in week 11, the UK National Ecosystem Assessment. And they had a whole list of things that we're interested in. Visual amenity, can you see a lake from your house? Can you see a forest from your house? Sports facilities, cultural heritage, health, and so on and so forth, education. They looked at 1 million housing transactions. They did not go to Rightmove because it didn't exist yet. Instead, they went to Nationwide. What I did not say, if you go to Rightmove or a website like that, you find the asking price. Not what people paid for it, but what was asked for it, right? And that's not necessarily the same. If you use mortgage data, you know the exact price that people paid for it. The disadvantage is that the bank does not store as much detail of the house as the real estate agent does. And it had a full postcode, not the address, but the full postcode, right? So that's typically a group of 10, 15 houses that you would know. And of course in the city that is pretty close together. They had basic characteristics of the house, they had the neighborhood values because they had the location, and all sorts of environmental variables as well. And one of the maps that they stuck in is this one. And I showed you this square before, now we have the entire map. This is what the landscape is like all over the UK. So we have the improved grasslands, we have the neutral grass, we have set-aside grass, I don't know what the difference is, and we have acid grass and calcareous grass, so this is on chalkland, and so it's pretty detailed, right? And you have all these maps, salt marshes, bogs, mountains, and so on and so forth, woodlands of their various types, and we know exactly what the UK looks like, right? In pretty great detail. They also use these maps. So here are the national parks. We're here, right? You see other locations of the national parks. These are the various components of the green belt. And then this one is harder to see because these are the National Trust properties, and you see dots here and there, but they're much, much smaller than the other two, and therefore this map is hard to see. And then they had the exact location, well, almost exact location of these houses, So you can calculate, you live here, your SOF, this is the closest National Trust property to you, right? You can calculate all these things and then run this regression of the sale price of the house on such things. And what you find is numbers like this. So if you're close to freshwater, the price of your house goes up by £768, right? If you're close to broadleaf forest, it's 377, but coniferous forest we don't like so much. It goes up to by 227, right? Farmland 113. Most importantly, English. If you live near gardens, your house price goes up by almost £2,000, right? So sort of manufactured nature is much more important than nature, right? If you live in a national park, your house price goes up by 9,400. If you live in the greenbelt, it's 6,000. If you live close to National Trust property, it drops. This is not because people don't like the National Trust. This is because so many people like the National Trust. So if you live near a National Trust site, then you have a lot of congestion, you have all sorts of idiots parking their car in front of your house, making lots of noise, and so on and so forth. Really, it's very nice, but you don't want to be near there, right? That is why this is a negative sign. And then you can add up all these things and say, well, this is the environmental value, the total environmental value as reflected in house prices. As you can see, we are pretty well off here. One of the highest prices, not quite as high as around here, but close enough, right? This part of the country is desperate for its environmental quality. The lowest is somewhere near Northampton. Somewhere here, right, in a natural environment, far away from anything that might look nice. And these numbers are large, right? Relative to the average, it goes from minus 33 to plus 83, right? So the exact same house that sits here would command half the price of a house that sits here, right? Almost done. So these things are important, right? And they can be done, right? We have here an estimate of the total environmental value in England, right? As expressed through the housing market. That's all I wanted to say. The final slide just sums up all the things that I've said already. I hope to see you guys tomorrow and Wednesday, where we're going to do one of these studies, and I'm going to take you through data to actually do it and interpret what is going on. Okay, I hope to see you guys then.